Okay, hi everyone, welcome to the exercise class. So today's exercise class, we will look at two topics. So first topic, we'll introduce Rènyi entropies, because first they were mentioned in class. They're useful for discussing thermal operations and resource theories based on thermal operations. And then we will look at something that was hinted in the lecture. We will look at thermal operations and which kind of second laws they induce. And we will see that if we put a certain restriction on the type of the thermal operations that we are allowed to carry, then it will single out a single second law, which is the second law that we're used to. Okay, so let me start with Rènyi entropies. And what are Rènyi entropies? If you took quantum information theory, you know that entropy of a system is a good way of kind of measuring the information that the system contains. It's also a good way to characterize things, how much work we can extract from the system and so on, which we'll see in the later in the lecture. But generally, when we are talking about entropy, kind of in a classical information theory, most of the time what we mean is Shannon entropy. However, Shannon entropy can be generalized to a broader class of entropies. So first we have Shannon entropy, then we generalize it. And these are called Rènyi entropies. And they're introduced the following way. So suppose that we have a probability distribution P, which is a vector. And then we label these entropies by alpha. So it's kind of their number. So S alpha of P is equal to -1 over alpha -1 logarithm sum from I equal 1 to M, where M is the size of the system, or the length of probability distribution, pi to the power alpha. And we see that this expression is well defined for all positive R's except for 0 and 1. So we'll treat these cases of 0 and 1 separately. So these few special cases then include 0, 1, and also we would like to introduce this entropy at infinity. So at alpha equals 0, this entropy is S0 of P. It's equal to log rank P, which makes sense because, so here we assume that 0 to the power of 0 gives you 0. So we are coming from this assumption, which means that if alpha equals 0, then the only terms that survive in the sum from I equal 1 to M are terms for which pi is non-zero. And each of these terms will give the contribution 1. And so the number of such terms is equal to the rank of P as a vector. So the number of its non-zero elements. And so we're, and then here alpha, if we input 0, it gives us -1, which colliding with this minus gives us just +1. And hence we just arrived to this expression. So this is kind of easy. For the case when alpha equals 1, actually we arrive to something that we're used to the Shannon entropy. This is less trivial to show. We will do it in a moment after I also introduce the entropy for alpha equal infinity. but we arrive to the thing that we're used to. By the way, the first S0 is also called max entropy. And for infinity, if we look at the limit of S alpha with alpha going to infinity, what we get is log max sum over I pi. This is also called min entropy. Okay. So now let us indeed check that for alpha going tending to 1, we indeed get the expression which corresponds to our usual Shannon entropy. So if we look at the limit, so let's write S1 of P is limit for alpha going to 1, S alpha of P, which is equal. So here I'm just rewriting the definition of S alpha of P. So we get minus here log sum pi to the power alpha over alpha minus 1. So what is the difficulty with taking this limit? So we see that as alpha tends to 0, both numerator and denominator tend to 0. So we're kind of looking at the limit of the expression, which is kind of 0 over 0. So the analysis, what analysis tells us that we have to do is to use one of these special rules for taking limits, for calculating limits, when we have the expression where both numerator and denominator tend to 0. And such rule is L'Hopital theorem. So L'Hopital theorem basically tells us that if we have...
Sorry,
yes.
May I interrupt? What was the definition again of S of alpha?
So the definition of S of alpha is following.
Yeah, sorry, I copied it wrong and then I had something weird. Okay, thank you.
No worries. Okay. So we use here the L'Hopital theorem, and the L'Hopital theorem basically tells us that sorry, is there something with the sound? Okay. So if we have two functions which are reasonably nice, f of q and g of q, and we want to calculate the limits of q tending to alpha, and it's such, and these functions f and g have derivatives, and also they tend to 0 as q tends to a, then this limit is equal to the limit of q tending to a, f prime of q, and g prime of q, which are the derivatives of f and g. So here, in taking this limit, we can use this theorem. So then S1 of P equals limits alpha going to 1. So the derivative of the denominator is 1. Then the derivative of the expression above is, so we get 1 over sum pi alpha. And here we get d by d alpha sum over I pi alpha. Okay, which gives us this limit and the expression here we just take a derivative as usual, expressing this power as an exponential. So this is e to the power alpha log pi. And so here we get the sum over I. Let me check if I'm doing everything correct. Yeah, the sum over I log pi to the power alpha. Okay, and so now we can safely assume that alpha equals 1. And what we get is minus sum over I pi log pi over sum over I pi. The expression below gives us 1, because this is just summing up over the probabilities in the probability vector. And the expression above gives us actually the entropy, the Shannon entropy. So we successfully proven that our Rènyi entropy that we introduced as alpha tends to 1 converges to Shannon entropy. Okay, so also one can prove that indeed the limit of S alpha of P as alpha goes to infinity equals minus log what was it? Minus log maximum over IPI. So this goes a bit different than this derivation. You just have to assume that, for example, P1 is the biggest one and then take it out of the sum, and then also then separate logarithm into this P1 part and also the remainder of the sum, and you'll get this result. Okay, what other properties do Rènyi entropies have? The same as Shannon entropy, they're also all Schur concave. And this can be proven in the same fashion as in the lecture it was proven that Shannon entropy was Schur concave. And also all Rènyi entropies are bounded. So the values that they take are all in between 0 for a pure state and log m for a maximally mixed state. So essentially properties. So first, all S alpha are Schur concave. And second, S alpha is always between 0 and log m. And this is because the probabilities are bounded. So in 0, it's for pure states, and log m is for maximally mixed states. So as you see, all the same as Shannon entropy, all of these Rènyi entropies are kind of nice, also nice measures to characterize information, because they're all Schur concave. They're also all clearly distinguished between two external points of pure states and kind of knowing everything about a state, and also maximally mixed states, which is essentially knowing nothing, or uniformly nothing, so to say. Okay, and the same as we can having Shannon entropy, we can introduce relative entropies. We can also introduce relative entropies in this generalized sense of Rènyi entropies. So we can have relative Rènyi entropies, which are defined as follows for two probability distributions P and Q. So 1 over alpha minus 1 logarithm of sum from 1 to m, pi to the power alpha, qi to the power 1 minus alpha. And the same as in the previous case, one can show that the limit of this expression for alpha going to 1 will give us expectedly the relative entropy in a sense of Shannon entropy, the one that we are used to. So it gives us pi I logarithm pi I over qi. So this is this relative entropy that we're used to. Okay, so this is a part of exercise. You have to show it, but since you already know the technique with which it's done for the Rènyi entropy, just usual entropy, not relative one. For alpha going to 0, this is fairly easy. Okay, so now we looked at the Rènyi entropies. Now the big question is, why did I tell you all of this? How does it relate to the topics that we're discussing in the lecture? And it relates in the following way, which also connects to the research, to the current research that's been done in the area of quantum thermodynamics. So that brings us to the second part on thermal operations and which restrictions we can put on the interactions in the systems. So one of the important thermodynamic quantities at the macroscopic scale, like in the usual thermodynamics, phenomenological thermodynamics, which is taught in like any physics bachelor course or in school, there is a very important quantity, which is the free energy. So the free energy is defined as E, which is the internal energy of the system, minus Ts, temperature and entropy. And this free energy has a very important meaning, namely, suppose that we're looking at the system which is kept at constant volume and also at temperature T, which essentially means that, it's in some closed container which has a continuous connection with the thermal bath at temperature T. So say constant volume plus thermal bath T. So the transitions which are possible for the system are the transitions between two states such that the change of free energy in these two states, so the free energy of the final state minus the free energy of the initial state, is negative. So transition between two states is allowed if and only if delta F is less or equal than 0. And this gives us a great characterization for all possible states the system can go to under the circumstances of being in a closed container at all moments connected to a thermal bath. Now the question we might ask ourselves is, okay, so this works for our usual macroscopic thermodynamics. Does this work for microscopic thermodynamics? The question is, it depends. Like this for microscopic thermodynamics, we might have not only one measure of free energy which could characterize its transitions, but we can have a whole family of such measures, which are called alpha free energies. Alpha family of free energies. And here yeah, you probably already start guessing that that's why I introduced this Rènyi entropies and labeled them as alpha. So they exactly connect to these families. But first, let me formally introduce the setting in which this is all happening. So yeah, let me be colorful here. So the setting is as follows. So we have a system, which we label A, with initial state row A. The Hamiltonian is HA. Yeah, and this is our system. What we also have is a machine. Suppose I'll draw it just as a machine and somehow working. And it has two things. It has a catalyst, which I here label as sigma m, and it has a work bit, which is initially in the excited state. What happens next? Next, we perform some energy preserving transformation, so energy preserving unitary on the whole system. And what we get in the end is, so the machine, it doesn't have work anymore, so the work bit goes to the ground state. The state of catalyst does not change. This is crucial. And the system ends up in a state which we label as rho A prime, the same Hamiltonian. So let me also write that this is the machine. Yeah, and this is the system. Also important assumption, as before, we always assume that all of these systems are in a constant contact with the thermal bath. So this is thermal bath. Yeah, according to my color, it may be cold, but yeah, let's see. Gamma B with Hamiltonian HB. So gamma B is just how I label the thermal state corresponding to this bath. Okay, so this is essentially the setting that we're looking at. And the first, the first observation, which has been shown in literature, is that the quantum, for the quantum systems, it is the possibility of the state transitions is not determined by the free energy alone. So for quantum systems, given this setting, it is not only the free energy, but it's this family of alpha free energies. And yeah, you can, if you're interested how one can show this, in the exercise sheet, I give a reference to the corresponding paper. So let me, a family of F alpha free energies determines whether a transition can happen. The key assumption of this model is that suppose that we forget about the work bit. If we forget about the work bit, the transition that the system is undergoing is yeah, and we also forget the thermal bath because we can always add and trace out the thermal bath, so it's not a problem. The transition that is happening is the following. So we have a state of the system and the state of the catalyst, sigma m, and it maps it to the state of the system, which is now rho a prime, and the state of the catalyst per this assumption does not change. I mean, that's why it's called the catalyst usually, because it's like when in a chemical reaction, you need to add a certain, for example, metal for the reaction to carry out, but the metal itself is not involved, or the reagent itself is not involved in the reaction, then that's what we usually call the catalyst. Yeah, and of course, maybe I should have mentioned this before, we assume that as in all other modeling, that the only operations that are allowed are thermal operations. So this has to be in energy preserving unitaries. We can always access thermal states, and we can always trace out over the degrees of freedom of thermal states, of the bath degrees of freedom. And so essentially this means that catalyst stays. Of course, one can think that when dealing with actual systems, this assumption may not make sense, because especially when we are dealing with quantum systems, because it's so easy to get a quantum system entangled with the other system, and it's kind of difficult to keep it separate, like still in this tensor state. But for here, we assume this. And then the condition is the same as the condition for a macroscopic case, but just for this F alpha energy for all alphas. So the change of free energy is equal to the free energy of the final state of the system minus the free energy of the initial state of the system. And it has to be, for the transition to be possible, it has to be negative for all alphas bigger than 0. So how we define this F alpha energy? So F alpha of rho A is KBT S alpha rho A gamma A minus KBT log ZA. So what are these things? So T is the temperature of the bath. S alpha is the relative Rènyi entropy that we have just looked in a previous consideration. Rho A is the initial state of the system. The state of the system. Then gamma A is the thermal state of the system A, given the temperature of the bath T. ZA is the how it's called, partition sum of the system A. And so partition sum just involves the energy levels of the system A. Okay, and for alpha equal 1, we can already guess that this free energy would probably just converge to the free energy, to the usual free energy that we're talking about in the microscopic case. So let me quickly show this. So for alpha equals 0, our relative Rènyi entropy will just turn into our usual relative entropy. And hence F1 of rho A will look as follows. So KBT S rho A gamma A minus KBT log ZA. So here, as in all other examples that we look at, we assume that rho A is diagonal in the energy basis. So here we can write this out as KBT sum over I Pi log Pi over Qi. So Pi are the diagonal elements of rho A, and Qi are the diagonal elements of the thermal state. Minus KBT log ZA. Then Qi, they are the diagonal elements of the thermal state. Hence, they have a specific form. So let me move this a bit lower. E to the power minus beta EI over ZA. So hence, we can write it as KBT sum over I Pi log Pi minus KBT sum over I Pi log Qi. And instead of Qi, let me already input this. And also minus KBT log ZA. So we see that some parts of this expression cancel out. So for example, this part of the logarithm and this expression cancel out. What we're left with is the following. We're left with KBT sum over I Pi EI beta, and beta cancels, sorry, just found a bug. And beta cancels out with KBT. So we're left with sum over I Pi EI plus KBT sum over I Pi log Pi. Yeah, sorry. Sometimes, most of the times, we assume that the Boltzmann constant is 1, as usually theoreticians assume that all constants are 1 and then never think about it often because we don't have to calculate anything. But yeah, let's say that this definition of free energy was up to this constant. But in any case, what we're left with is the average energy minus T S of rho A. So we arrive to our usual Helmholtz free energy. So we see that for alpha equals 1, this is just our usual free energy. This was just a small discourse, again, showing that the free energy is just the particular case of this family of alpha free energies.
Sorry, I have a question. In the step that you cancel out the logarithm of ZA,
yes.
In the first term, what are we summing over? Because the way that I see it, we shouldn't be able to just cancel it out that easily.
Okay, so the way I cancel it out here is, so we can take this expression and then we can, within the sum, rewrite this as Pi logarithm e to the power minus beta EI minus Pi ZA. Sorry, logarithm ZA, right?
Yes, got it. Okay.
And then sum over Pi here gives us 1 because it's a probability distribution, essentially.
Yes, absolutely. Thank you very much.
You're welcome. Okay, So again, coming back to the point I was making is for the microscopic case, when we consider the case when the catalyst has to stay separate in a separable state with the system, the transition is determined by this whole family of free energies. However, we can consider a bit of a different transformation of the state, such that it would single out only one particular free energy as a transition characteristic, as a transition necessary and sufficient condition. And this is a following. So let me copy this picture I made here. And put it here again. So we're looking at the same picture with the machine, system, work bits in the machine, and the thermal bath. They're all swimming it. And the only thing that we allow for is, only thing we change is that we now have some correlations between the machine or the catalyst and a system. So we allow for some correlations. What does that mean? So we're now looking at the transformation, which takes rho A tensor sigma m to the joint state sigma am, such that we consider the final state of the system rho A prime as the tracing out m out of this joint system. And we also assume that the state of the catalyst does not change, but it doesn't change kind of up to the correlation that it shares with the system. So it's like we start with the state of the catalyst sigma m. We end up with the catalyst being in an entangled state with the system, or correlated with the system. Sorry, correlated with the system. It's not necessarily entangled. But it should stay the same if we trace out the degrees of freedom of the system. So sigma m should be still equal to tracing out the system A from the joint state of the system and the machine. So now this class of transitions only allows for alpha equal 1. So if we consider which, if we're trying to find a measure which would tell us whether a particular transition can happen or not, it would be only our original free energy, which we also use in macroscopic case. And this would also make a lot of physical sense, because the transition that we were initially looking at, where the catalyst, the machine, would stay uncorrelated with the system, is physically very unrealistic. So of course we can still artificially make it happen, but usually this is during the interaction, some degrees of freedom do get correlated. Okay, and so this is essentially the message of the second exercise. In the second exercise, you'll again walk through like some of the small sub-exercises of what I was just talking about. And then you also see how imposing the initial, like looking at the initial scheme of the catalyst kept uncorrelated with the system, imposes certain restrictions on the work bit. So here we assume that the work bit has some energy gap delta between its two levels. And if we consider the family of alpha free energies as our transition characteristic, then for the change of this free energy to be negative for all alpha, there are certain restrictions that have to be imposed on the energy gap of the work bit, which is also which also tells us that, like, so for some energy gaps of this work bit, this procedure would be, some procedures would be not efficient. However, when we turn to the case where we're allowed to use these correlations, or not use, but kind of create correlations, then essentially what happens is that even if the catalyst, the sigma m is just a single qubit, then we are able to increase efficiency comparing it to the case when we are not allowed to create any correlations between the system and the catalyst. But these are just two small computational examples. And if you're interested more in in how these things are proven in general, then I left you two references to the papers. The first one, which shows that the alpha free energies are actually a sufficient criterion for the transition, sufficient and necessary. And the second paper, among other things, it shows that indeed imposing this correlation condition does single out only one energy, only one free energy out of this family. Okay, I think I was talking for a long time, so that's it for today. Yeah, if you have any questions, feel free to shoot or write it on a forum or on an email, whatever, or also come to the office hours.